Okay, so let's go to our textbook, section 2.1, entitled The Rectangular Coordinate System and Graphing Utilities. First thing we're going to do is just quickly review the XY plane. Being a course in college algebra, ladies and gentlemen, you should have been introduced somewhere along the line to the XY plane. If you've never worked in the XY plane ever before, those previous courses failed you, or you were just in the wrong course here. Anyways, we have the horizontal number line is called the x-axis normally, but it can take on any number of names when you apply these graphs to sciences in the real world. The vertical axis is normally called the y-axis, but again, it can take on a myriad of names. Normally, tick marks are spaced 1 unit apart on both axes unless indicated otherwise. The bottom line is, regardless of the spacing of your tick marks on both axes, they have to be linear scales. Okay. The intersection point of the XY coordinate plane is called the what? Called the origin. Its ordered pair address is 0, 0. And what we do in the XY plane, ladies and gentlemen, is we plot points and we graph relations and or functions in X and Y. Of course, ordered pairs have a specific ordered address about them. The X coordinate precedes the Y coordinate always. And notice the X and Y axis splits up our plane into 4 quadrants. This is quadrant number 1, bounded by the positive X and the positive Y axis. Quadrant 2, bounded below by the negative X axis and to the right by the positive Y axis. Quadrant 3, bounded by the negative X and negative Y axis. And quadrant number 4, bounded by the positive X and the negative Y axis here. Okay, next thing here, plotting points. Do we all know how to plot points in the XY plane? You always start at the origin to plot points. So to plot the point -2, 0, you start at the origin. And if its X coordinate is -2, you move 2 units to the left on the X axis. Y coordinate 0, you stay right on the X axis. That's -2, 0. 0, 3, starting at the origin, you do not move right or left on the X axis. You just move up 3 units on the Y axis, plot the point, 0, 3. 4, -2, start at the origin, move 4 to the right on the positive X axis, and then move down -2 units parallel to the Y axis, -1, -2, and there's 4 and -2 in quadrant number 4. Sometimes your ordered pairs might have decimal or fractional coordinates. It does happen. This ordered pair has an X coordinate of 2.5. If you project it straight down to the X axis, it gets 2.5. Projected horizontally to the Y axis, it strikes 3.5. All right, ladies and gentlemen, any questions about how we plot points in the XY plane? Are we good on that? Okay, now what I would like to do is introduce ourselves to what is called the distance formula in the plane. Okay, so that's the next thing I'm going to do here is we're going to derive what is called the distance formula. And we'll also look at what's called the midpoint formula. All right. Here's my XY plane here. Suppose that I have 2 unique points in the first quadrant. And I put a line segment connecting these points. I will call this point here X sub 1, Y sub 1. I will designate this point up here as X sub 2, Y sub 2. Since the subscripts are different, these points are unique. They're not the same. Okay, so what I'm going to do is I'm going to build a little right triangle here. Now we got a right triangle. And later on, we're going to find a formula that will enable us to compute the distance between 2 unique points in the plane. So that's what we're going to do is derive what's called the distance formula. And it can be used for any 2 points in the plane, not just in the first quadrant. Okay. All right, if I project this point X sub 1, Y sub 1 straight down to the X axis, I strike what tick mark? I would strike X sub 1. If I project this point X sub 2, Y sub 2 straight down to the X axis, I strike the tick mark X sub 2. If I project this point horizontally back to the Y axis, I strike the tick mark Y sub 1. And if I project this point horizontally back to the y-axis, I strike y sub 2. Does this drawing make sense so far? Okay. So ladies and gentlemen, what would be the length of this leg of my right triangle here? Well, the length of this leg of my right triangle is going to be the difference between the x coordinates. So we'll say x sub 2 minus x sub 1. The length of this leg of my right triangle is going to be the difference between the y coordinates, y sub 2 minus y sub 1. We'll call the length of the hypotenuse, the longest side of my right triangle, we'll call its length d. All right. Now, because we have a right triangle into play, we can bring a useful relationship that's been around for thousands of years. It's called the Pythagorean theorem, or the Pythagorean relationship, that involves the relationship between the lengths of sides of a right triangle. So, ladies and gentlemen, if you have a right triangle, it must be true that if you take the longest side, the hypotenuse, and square its length, that must always be equal to the sum of the squares of the lengths of the legs. So therefore, the length of this leg is x sub 2 minus x sub 1. We're going to square that, and then we're going to add it to the square of this length of this leg of our triangle. Now, solving for d, the distance between these two unique points, we just take the positive square root of both sides, and we have derived, ladies and gentlemen, what is called the distance formula in the plane. So this formula here will give you or compute the distance between any two unique points in the xy plane. It is called the distance formula. Any questions about how we derive that formula? All right. Another useful formula that we're going to derive is called the midpoint formula. It will enable us to compute the midpoint between these 2 points, x sub 1, y sub 1, and x sub 2, y sub 2. I'll call that point M. Okay, so how would we compute the midpoint of this line segment, point halfway in between these two endpoints? Well, if I drop a perpendicular straight down to my x-axis from this midpoint, I would strike a value on the x-axis that's halfway in between x sub 1 and x sub 2. Ladies and gentlemen, how do you find the average or the midpoint between two numbers? Well, you just add them up and divide by what? 2. So that's going to be the x coordinate of my midpoint. And then if I take the midpoint horizontally, project it back to the y-axis, it strikes a value on the y-axis and be halfway in between y sub 1 and y sub 2. So therefore, this value is going to be the average of y1, y2. And this would be the y coordinate of our midpoint. Therefore, our midpoint formula, M for midpoint, to find the midpoint between any 2 points in the plane, 2 unique points, the x coordinate will just be the average of the x coordinates of the 2 endpoints, and the y coordinate is going to be the average of the y coordinates of the 2 endpoints. This is called the midpoint formula. Any questions how we derive either the distance or the midpoint formula? Okay. All right. Let me know when I can move on. Everybody have this accounted for? Again, this video is being recorded, so I will make it available if you miss anything. All right, so let's put these formulas to work. Ladies, I want to know how to compute the distance between 2 points or the midpoint. And here's a beauty here. This is on page 173 in your textbook. It's problem number 12A and B. They want us to compute the distance and the midpoint between these 2 points here. -1, -3, 3, -7. Okay. Now it doesn't matter which point you call your first and second point. You could call this your x1, y1 point, or this one your x1, y1 point. Doesn't matter. I will designate this as being my x1, y1 point and call this my x sub 2, y sub 2 point. All we have to do to find the distance between these points is just plug the values in to your distance formula. So the distance between these points is going to be the positive square root of x sub 2 minus x sub 1 squared. So x sub 2 is 3, minus x sub 1 is -1. Careful with your signs, as always. And we're squaring that. And we're going to take y sub 2 minus y sub 1 and square that. So we'll have -7 subtract a -3, -7 minus a -3 and we square that. And now we go through the arithmetic here. 3 subtract a -1 is 3 plus 1, and that's 4. 4 squared is 16. -7 minus a -3 is -7 plus 3, which is -4. -4 squared is what? Plus 16. So it appears that the exact distance between these 2 points in the plane is the square root of 32, which you can simplify. The square root 32 is not a perfect square of a whole number. However, 32 can be rewritten as 16 times 2, and 16 is a big perfect square of 4, the square root of which would be 4. So this would be the exact distance between those points in a plane. And normally your author in your textbook wants you to leave your distances in exact form. I mean, you could get on a calculator, dial this up, or even take the square root of 32, it would give you a decimal approximation, but we'll leave this as such. What would be the midpoint between these 2 points? Well, the x-coordinate of which has to be the average of the x-coordinates of the endpoints. So the x-coordinate is going to be x of 1 plus y, x of 1 plus x of 2 divided by 2. And the y-coordinate will be the average of the y-coordinates of the 2 endpoints, -3 plus a -7 divided by 2. So it turns out this midpoint is going to be, what's that? 2 divided by 2 is 1. And -3 plus -7 is -10 divided by 2 is -5. Ladies and gentlemen, this point here would be halfway in between these 2 points. It's called the midpoint. Oh, yes, and I will make sure that I post the lecture from Monday. I thought I did that. Okay, it slipped my mind, but I'll make sure I do that right after this session. Okay, thanks for reminding me. Any questions, ladies and gentlemen, how we applied the distance and the midpoint formula to 2 unique points in the plane? Okie dokie. All right. The next major order of business in section 2.1 is learning how to, graph various functions or relations in the plane. Okay. So the next thing we're going to do is we're going to visit the plane and graph relations or functions. Now, in the next section, we draw a distinction between a relation and a function. I'm just kind of throwing these terms around right now. So what we're going to do is we're going to try to graph this equation that embodies 2 different variables, x and y. It's a relationship between x and y. It is not a linear relationship because x is raised to the 2nd power. We call this a quadratic relationship in x. And we're going to try to graph this. As it turns out, it is a function. To do that, a popular method is to use what's called your table method. So what we'll do is we'll build a little table here. And the first column of which I will label as my x column. And my second column will be my y column here. I also like to have another column, which is my ordered pair column. Okay. So, ladies and gentlemen, the name of the game here is you can choose any value for x, plug it in and solve for y, or any value for y, plug it in and solve for x. It's up to you. Normally, we choose values for x, substitute them in, and then solve for y. For plotting purposes, you want to choose nice values for x. You don't want to choose messy fractions or decimals if you can help it. And you don't want to choose values too far away from the origin. Like you don't want to choose x to be like 1,000. I mean, good luck in plotting that point, correct? Or you don't want to choose x to be like -1,000 or something like that. So what I'm going to do is I'm just going to, choose some nice values kind of close to the origin. And here we go. And we're going to crank out some ordered pair solutions to this equation in x and y. First, we're going to let x be equal to -3. So if x is equal to -3, we have to substitute -3 into our equation to solve for y. So if x is -3, in goes -3 in for x. So we'll have -3 squared plus y equals 1. We'll have negative 3 squared is 9, so 9 plus y equals 1. Solving for y by subtracting 9 from both sides, we get y is equal to negative 8. So one ordered pair solution to this equation in x and y is this ordered pair negative 3, negative 8. So this point's going to have to lie on the graph of this equation, correct? If x is equal to negative 2, what's y going to be? Replace x with negative 2 in the equation and solve for y. Negative 2 squared is going to be 4. 4 plus y equals 1. Subtracting 4 from both sides, we get y is equal to negative 3. There's another ordered pair solution, another point that would lie on the graph of this equation. When x is equal to negative 1, replace x in the equation with negative 1, solve for y. Negative 1 squared is 1. Subtracting 1 from both sides, we get y is equal to 0. So negative 1, 0 would also be a solution. If x is 0, as 0 is easy to work with. What's y going to be equal to when x is 0? If I put 0 in here, this term's gone. And we're left with y equals what? 1. If x is equal to 1, equally easy. 1 squared is 1. 1 plus y equals 1. Subtract 1 from both sides. Y would be 0. If x is equal to positive 2, what's y going to be? Y will be equal to negative 3. Any questions how we generated those ordered pair solutions to that equation there? All right, next thing we're going to do is we're going to take a piece of graphing paper, and I will post this piece of graphing paper on Canvas, and you can do whatever you want with it. Okay, if you want to get a tablet of graphing paper at a store, you can do that also, but please try to get your hands on graphing paper for chapter 2. So what we got to do now, liaisons, we have to plot all these points here in the XY plane. And let's see if I can fit all this on one screen here. So this is my x-axis, and this is my y-axis. Please put arrows on the ends of your axes, very important. We will assume that the tick marks are spaced 1 unit apart on both the x and the y-axis. All right, so let's plot these points. Negative 3, negative 8, we start at the origin. To plot negative 3, negative 8, this first ordered pair solution of our equation, we move 3 to the left on the x-axis, negative 1, negative 2, negative 3, and then we move down 8 units, negative 1, 2, 3, 4, 5, 6, 7, 8, right here. There's negative 3, negative 8, lies in the third quadrant. Plotting negative 2, negative 3, starting at the origin, we go 2 to the left on the x-axis and then down 3, negative 1, negative 2, negative 3, there's negative 2, negative 3. You know, you can label these points if you want to. It does clutter your graph up, but, feel free to sneak the ordered pair address next to the point if you want to do that. And this would also be negative 2, negative 3. Negative 1, 0, starting at the origin, we go 1 to the left and we stay right on the what? Right on the x-axis. There's negative 1, 0. Negative 1, 0. 0, 1 is going to have a start at the origin, move just up 1 unit on the y-axis, 0, 0, 1. 1, 0, starting at the origin, we move 1 to the right, there's 1, 0. 2, negative 3, started at the origin, move 2 to the right and down 3, negative 1, negative 2, negative 3. You see this point got in the way here? It happens. Okay. So I didn't put the point really in a great place there. Labeling the points is both nice and can be a problem if you put them in the wrong place. So 2, negative 3, 1, 2, 3, we're right down here. All right, so we plotted these points. Can you kind of see what this graph is going to do, ladies and gentlemen? It's obviously not a line graph. That's to be expected since this is not a linear relationship between x and y. So the graph is going to be some sort of a curve. And as it turns out, the graph is going to be what is called a parabola that opens downwards. So it's going to be a parabolic graph that definitely does open downwards. And you can see that this graph is symmetric with respect to the y-axis, in the sense that if you were to fold this graph about the y-axis, the branches would mesh up perfectly. Okay. All right, so that's the graph. That's how we graph that quadratic relationship manually using a table and cranking out ordered pair solutions and then plotting them. Another way to graph this equation is to use your graphing calculator. But in order to use your graphing calculator, ladies and gentlemen, we have to solve the equation for the y variable. And so how would I solve for y here? Anybody? How do I solve for y? How would I solve this for y? Let's see.
You would move the x.
X what? Squared? How do I move x squared to the other side? You're right. How do I move this x squared to the other side?
Square it.
Well, I got to move x to the other side. I got to get y by itself. And we'll solve for y here.
You subtract the x squared, and then you square it.
All right, let's subtract x squared from both sides. And we subtract from the left, it's gone. And on the right side, we'll just report it as 1 minus x squared. Or you could say y is equal to negative x squared plus 1. Same thing. All right, ladies and gentlemen, let's take this to our graphing calculator and throw it into our TI-84 and see what the machine can do for us, okay? So here we go. We're going to take that equation to the calculator. Uh-oh, somebody has a message for me. Sorry about being late. I was having computer problems. That's okay. Computers have snow days too. All right, here we go. Hopefully all systems go with the technology. So we're going to try to graph this. We're going to try to graph this equation, ladies and gentlemen. Hit your y equals button, go to your equation editor. We need to type the equation in. Y is equal to negative x squared plus 1. Negative, hit your negative button. Your x button is above, is just to the right of your alpha button. X, and then you want to square that. You can hit your x squared button, or you can hit your general power button and say raise to the second power. You must hit your right arrow key to bring the cursor back down to level. Plus 1. So we've typed in that function, that equation, and we're good to graph this thing. I'm going to look at my window setting here to see what kind of scaling I got going on my X and Y axis. So I'm going to hit window. Notice my X and Y axis is configured to run from -10 to 10 by 1 for a min to a max value, and the spacing between tick marks is 1 on both axes. That's a good scaling. Let's go with that. Hit graph now in the upper right corner of your keyboard, the graph button, and you should see the graph of that parabola. Did we all get that graph, ladies and gentlemen? Anybody having a problem getting that graph? Notice the graph is the same as what we obtained manually here. Okay. All righty. So I'm assuming we're good on that graph there. All right. Okay. Let's go back and try another one here. Let's try to graph this relationship here between X and Y. The absolute value of X minus 3 minus Y equals 4. We're going to try to graph this equation in X and Y. It is an absolute value relationship between X and Y. We can use the table method again. We can generate some ordered pair solutions. I'm going to choose these values here, 0, 1, 3, 4, 6. Okay. This let x be 0 and find what y would be. So if x is equal to 0, we'll take 0, substitute it in for the x variable into our equation and solve for y. So we have the absolute value of 0 minus 3 minus y equals 4. 0 minus 3 is -3. The absolute value of 3 is going to be what? 3. 3 minus y equals 4. And now we have to solve this equation for y. We could subtract 3 from both sides and then divide both sides by a -1. And we should get positive. We should get -1. So this would imply that y is equal to -1. So we have an ordered pair solution to our equation. So this point would be expected to lie on this graph. When x is equal to 1, what's y going to be? Put 1 in for x. 1 minus 3. Absolute value 1 minus 3 minus y is equal to 4. 1 minus 3 is -2. The absolute value of -2 is 2. Now we just solve for y. Subtract 2 from both sides and then divide both sides by -1. Then we get x and we get y is equal to -2. Here's another ordered pair solution. Let x be equal to 3. Therefore, we have the absolute value of 3 minus 3 minus y equals 4. The absolute value of 0 minus y equals 4. Negative y equals 4 implies that y is equal to -4. Another ordered pair solution. Let x be equal to 4. Hence, we have the absolute value of 4 minus 3 minus y equals 4. 4 minus 3 is 1. The absolute value of 1 is 1. And just solving for y now, subtracting 1 from both sides, dividing both sides by a -1, we get y is equal to -3. -3. Another ordered pair solution. Finally, if x is equal to 6, we will have the absolute value of 6 minus 3 minus y equals 4. The absolute value of -3 minus y equals 4. Absolute value of 3 is 3. 3 minus y equals 4. Solving for y, subtracting 3 from both sides, we get 1. Negative y is equal to 1. Multiplying by a -1 or dividing by -1, we get -1. So 6 -1. There we go. We have several ordered pair solutions to that equation. We can now plot those points and start to see if we can determine what the graph has to look like. Okay. Any questions how we generated those ordered pair solutions for that equation there? All right. Again, whatever values you choose for x, try to keep them close to the origin for plotting purposes. All right, so we'll go to our graphing paper now, and we'll try to plot these points. There's my x-axis. 0, -1, plotting 0, -1 here. We start at the origin, and we just go down 1 on the y-axis. 0, 0, -1. Okay. 1, -2, start at the origin, go 1 to the right, then down 2. Did I do it again? I put the darn point in the wrong place again. You don't have to label your points if you don't want to. They do clutter your graph up. Okay, 1, -2, 1 to right, down 2, right there. 3, -4. 3, -4.
You really about to have me in this fucking online shit for too fucking out.
Okay, plotting the point 3, -4. We go to the right 3 units and then down 4. Right here. 4, -3. Start at the origin, go 4 to the right. 1, 2, 3, 4. -1, -2, -3. Right here. 6, -1. Start at the origin, go 6 to the right. 1, 2, 3, 4, 5, 6, and then down 1. And it kind of looks like this graph is going to look like a what? Anybody want to take a wild guess? It's not a line. A U-shaped graph? Well, it won't be a U-shaped graph. Those are reserved for quadratic relationships. This is an absolute value relationship. It's going to be a V-shaped graph. So you're going to have a real sharp kink down here. And this V-shaped graph is going to open upwards. So absolute value functions, ladies and gentlemen, have V-shaped graphs. This one opens upwards. And that would be the graph of that absolute value equation there. Any questions how we graph this manually here? By generating ordered pair solutions for that equation and then plotting the points and getting the graph. Okay. All right, let's try to do this now by using the calculator. To do that, we're going to have to solve this equation for y. And how would we solve this equation for y? Well, to solve the equation for y, we could, do it a couple different ways. We could subtract this entire absolute value from both sides to take it over to the right side. That would definitely serve the purpose. Therefore, we have negative y is equal to 4 minus the absolute value of x minus 3. Multiplying or dividing both sides by a -1, we have y is equal to -4 plus the absolute value of x minus 3. Feel free to even spin these around and call it the absolute value of x minus 3 minus 4. Okay. All right. So let's take this to the graphing calculator and plug it into our equation editor and graph this absolute value equation. So that's what we're going to plug into our graphing calculator. Go to y equals, clear out any garbage. Now we're going to type in the absolute value of x minus 3. Where is the absolute value function on the calculator? You have to hit your math button, ladies and gentlemen, math. And you go over to number, math, hit your right arrow key to go over to number. And it's your ABS function right there, absolute value. Hit enter. So we got the absolute value of x minus 3. Here's your x button. Subtract 3. Got to hit your right arrow key to get out from inside the absolute value symbols. And then subtract -4. That should do it. Now we should be able to graph this absolute value function. Hit enter, or graph rather. And we do see that V-shaped graph definitely opening what? Upwards. Agree? Everybody getting that graph? Everybody getting that graph there? Okay. So what we're doing is we're graphing equations manually by generating ordered pair solutions. All right. When we work with graphs or functions or relations, oftentimes we're interested in a couple of points. And those points have names. They're called the x and the y intercepts of the function or the graph. So what is an x and y intercept? Well, quick recalling here. Suppose that we had the graph of a line in the xy plane, the graph of a linear function. Ladies and gentlemen, the point of intersection between the graph and the x-axis is called the x-intercept. X-intercept. The point of intersection between the graph and the y-axis is called the y-intercept. Now, notice an x-intercept is always a point that lies on the x-axis. Therefore, since it lies on the x-axis, the y-coordinate has got to be equal to, what do you think? Anybody? What must the y coordinate of an x-intercept always be equal to? Anybody want to take a guess? Well, if a point's going to be on the x-axis, the y coordinate has got to be equal to 0. Otherwise, that point's not going to be on the x-axis. Y-intercepts lie on the y-axis, therefore its x-coordinate must always be 0. Otherwise, it's not going to be on the y-axis. So this provides a way to find x and y-intercepts. You always set the other variable equal to 0. To find an x-intercept, you set y equal to 0. To find a y-intercept, you set x equal to 0. All right, let's go to page 174 in our textbook. Page 174. All right. Okay. Page 174, I want to go over 45 through 50. All right, they want us to estimate the x and y intercepts from the graph. So problem number 45, can somebody give me the x-intercepts for this circle graph here? X-intercepts. Devin, what do you think? What would be the x-intercepts of this graph? X-intercepts.
9 and -1.
-1 right here and +9. So -1, 0 and 9, 0. All right, Cameron, can you give me the y-intercepts? Y-intercepts. You with us, Cameron? Kennedy, can you give me the y-intercepts? Lauren, can you give me the y-intercepts? Peyton, can you give me the y-intercepts?
Is it 3 and 3?
3 is one of them. You got that right. 0, 3. There's another one. What is it?
Oh, 0, -3.
Yeah, 0, -3 down there. Okay, good deal. All right, here's another circle. The x-intercepts would be 4, 0, -16, 0. The y-intercepts would be 0, 8. Looks like 0, 8. And 0, -8. All right, number 47. Does this graph have a y-intercept?
No, it doesn't.
There is no y-intercept.
It has an x-intercept, but not a y.
Yeah, an x-intercept would be what, -2?
Yep.
In fact, the x-coordinate of any point on this line would be what, -2, wouldn't it? All righty. How about this one? Does this graph here have a x-intercept?
Nope, it has a y, but no x.
Yeah, y-intercept would be 1, no x-intercept. This is a parabola that opens to the right. What would be the x-intercept?
0.
0, 0.
Mhm.
And notice that's also the y-intercept, correct? All right. This is an ellipse, and the x-intercept and the y-intercept would be 0, 0. And there's also another x-intercept of 6, 0 there. All right. So are we good on x and y-intercepts, ladies and gentlemen? I'm assuming we
Yes.
are. Okay. Okay. Now that's how you find x and y-intercepts, graphically. What if we're given the equation and we're being asked to compute the x and y-intercepts? Well, I mean, you could graph the relationship and use your calculator to find intercepts, of which I'll show you in a second, but we should also be able to compute them manually. So let's try one out here. Let's try to find the x and y intercepts for -2x plus 4y equals 12. This is just a linear equation, an x and y, the graph of which would be a straight line. To find the x-intercept, I'm going to set y equal to 0. Take 0, substitute it in for the y variable. Our equation collapses down to this right here. Now we just solve for x. This is gone. So we're left with negative 2x equals 12. Divide both sides by negative 2, and x comes out of this with a value of negative 6. So the x-intercept is negative 6, 0. To find the y-intercept, we set the other variable, namely x equal to 0. Take 0, substitute in for the x variable into the equation. And then what we can do is we can solve for y. This is gone. Divide both sides by 4, and y is equal to 3. So our y-intercept would be 0, 3. All right, that's how we find our intercepts manually. And now I want to show you how we can use our graphing calculator to find the x and y intercepts. But to do that, we're going to have to solve this equation for y first. And that's always been my pet peeve with graphing calculators, is that your equation has to be in explicit form, where y has to be solved in terms of x. Anyway, solving this equation for x, we would add 2x to both sides. Then we divide both sides by 4. Therefore, we'd have y is equal to 3 plus 1/2 x. Spinning this around, putting this in the slope-intercept form. That would be our equation solved for y. So now, ladies and gentlemen, we're going to take this to the graphing calculator, type it into our equation editor, and then I'll show you how to find the x and y intercepts. All right, here we go. We're going to take this to the graphing calculator. All right, I'm going to type in this linear equation, which is 1/2 x. I'm going to put the 1/2 inside parentheses here. 1 divided by 2, 1/2 x plus 3. Very important that you do put the 1/2 inside parentheses here. Now, when we hit graph, after typing that linear equation in, we get a straight line graph. Now we're going to find the x and y intercepts of this graph. To find the x-intercept and the y-intercept, we have to go into our calculate mode. Above your trace button, it says calc. That's your calculate mode. So we're going to hit our second button, followed by trace. And then we're going to go down and use the 0 function to find our x-intercept. Because as we're going to discover later on in this course, an x-intercept is really called a 0. So as we select the 0 function, always to find x-intercepts. Hit enter. And to find our x-intercept here, your calculator wants what's called a left bound. So navigating this blinking cursor on your graph so that it's a little below the x-axis, so that it projects up to the x-axis at a point that's to the left of our x-intercept we're trying to find. This is called a left bound. X-intercept's right here. Hit enter. Now your calculator wants us to establish a right bound. So by virtue of the way this graph slants as it goes to the x-axis, we have to navigate our blinking cursor so it's a little bit above the x-axis, so that that blinking cursor projects down to the x-axis at a point that's to the right of the x-intercept we wish to find. That's why it's called a right bound. Hit enter. Now hit enter again, and boom, your x-intercept is negative 6, 0. Everybody see that there? That's your x-intercept. To find the y-intercept, we go back to calculate, second trace, but this time we use the value function. So the value function always finds y-intercepts. Hit enter to activate the function, and we know that the x-coordinate of the y-intercept must always be 0. So we just type in 0, hit enter, and boom, you got your y-intercept, 0, 3. Any questions, ladies and gentlemen, how we find the x and or the y-intercept graphically?
So how did you do the y-intercept again? Can you show that again?
I went to calculate, so I hit my second, with my graph showing, I hit second trace to get into calculate, and then I use the value function. The value function is used to find y-intercepts. The 0 function finds x-intercepts. So let's hit enter. Then we always type in what for x to find a y-intercept? We always type in 0. Hit enter, and then your calculator will find that y-intercept. Did that help out?
It did. It did. Thank you.
Okay. All right. That's how you can find X and Y intercepts using your graphing calculator. Ladies and gentlemen. Let's go back and try to find some X and Y intercepts manually again, as we're moving closer to classwork 1. So we're right on schedule here, thank goodness. So I want to try to find the X and Y intercept, or SEPs, whatever the case might be, for this equation, x squared equal to negative y plus 16. So how would we algebraically find the X and Y intercept, or SEPs, for this equation? How would we find the X intercept? What do we always set equal to 0 to find an X intercept? We always set the other variable, namely y, equal to 0. Take 0, substitute it in your equation for y, and then we'll have to solve this equation for x. Hence, we're going to have to solve x squared equals 16 for x. To do so, we take the square root of both sides of this quadratic equation. Don't forget to take the plus or minus square root of the number side. Hence, we get x is equal to positive or negative. The square root of 16 is 4. So we get two x-intercepts. One is going to be 4, 0, and the other one's going to be negative 4, 0. Those would be your x-intercepts of this graph. To find the y-intercept, we set x equal to 0. Take 0, substitute it in for the x variable, and then solve the equation for y. Add y to both sides, you get y equals 16. So your y-intercept would be 0, 16. And there's your y-intercept. Any questions how we found the x and y-intercepts for that equation, or algebraically? And ladies and gentlemen, if you wanted to find these graphically, first you'd have to solve this equation for y. The way of doing that is to add y to both sides of your equation and subtract x squared from both sides, in which case you would then end up with your equation solved for y. Let's take this to the graphing calculator, and let's graph that quadratic function. Okay, so we're going to graph y equals negative x squared plus 16. Go to your equation editor, clear out any garbage, and then type in the equation. So we have negative x squared plus 16. And now we want to graph this quadratic function here. Hit graph, and you should see a parabola opening downwards. All right, we got to go up a little bit higher on our y-axis to see the vertex point way up there at the top. So therefore, we're going to have to go to our Windows setting and adjust the y max value to a little larger value. So I'm going to take y max up to 20 here. Now, when we hit graph, we should be able to see our graph with its vertex point there. All right, to find the x-intercepts, we're going to go where? What function do I go to find x-intercepts? Do we remember? Do we remember? X-intercepts, how do we find them on the calculator?
Is it second calc?
Second calc, second trace gets us in the
Yeah.
calculate. And then we go down and use what function to find x-intercepts?
0.
Zero function. Now notice your calculator is going to screen for the left and right bound business again. And the x-intercept you want to find, you have to move your cursor in that vicinity. So if you want to find this x-intercept to the left here, which you can probably just read it right off from the graph, but there's going to be occasions when we solve equations graphically, ladies and gentlemen, whereby the solution or the x-intercepts are not going to be readable from the graph. This one is obviously -4, and you can see this one's +4. But I'm showing you how to find them graphically so that we can handle difficult cases in the future. So I'm going to navigate my blinking cursor by repeatedly hitting my left arrow key and bringing that blinking cursor down below the x-axis. Why below? Why not above? Well, because if you bring your cursor down below on the graph, by virtue of the way the graph slants as it moves through the x-axis here, this blinking cursor projects vertically upwards to a point on the x-axis that's to the left of our x-intercept. Hit enter. We'll establish that as a left bound. Navigating your blinking cursor above the x-axis. Notice my cursor now projects down to the x-axis at a point that's to the right of my x-intercept. We'll call that a right bound. Hit enter. You see your calculator has to box in your x-intercept to go through numerical routine behind the scenes very quickly to zero in and find that x-intercept. Hit enter again, and there's one x-intercept, -40. To find the other x-intercept, we have to go back to calculate, second trace, go down and grab the zero function, but this time we have to navigate our blinking cursor in the vicinity of the other x-intercept. So bring it around over here. Now they want a left bound, but ladies and gentlemen, the graph slants differently as it goes through the x-axis now. So left bound will have my cursor being above the x-axis because the cursor projects down to the x-axis at a point that's to the left of the x-intercept. That's why it's called a left bound. Hitting your right arrow key, navigating the blinking cursor below the x-axis, that we will establish this as a right bound. Hit enter. We have boxed in effectively that x-intercept. Now, as we hit enter again, your calculator will go through some numerical routine behind the scenes to get that x-intercept, and it does come out to be 40. Finally, the y-intercept. How do we find the y-intercept? Anybody remember the function? Y-intercept. Y-intercept. Where does the y-intercept hang out? No. Calculate mode, second trace, use the value function. Type in 0 for x, hit enter. There's your y-intercept, 0.16. Ladies and gentlemen, the question is how we're computing x and y-intercepts both algebraically and graphically. Any questions? Let's try another one. Let's try an absolute value equation. So let's try to find the x and y intercepts for this one. So y is equal to the absolute value of x minus 5 minus 2. To find the x-intercepts, we always set the other variable, namely y, equal to 0. So y gets set equal to 0. Therefore, we now have to solve this absolute value equation for x. How do we solve absolute value equations? We have to isolate our what? Absolute value. And we will do that by adding 2 to both sides of our equation. And now that we have our absolute value isolated, we can drop the absolute value and place what's inside the absolute value equal to the positive 2, or we will set it equal to -2. And now we have 2 linear equations to solve. Adding 5 to both sides here, we get x is equal to 7. That's one x-intercept, 7, 0. Adding 5 to both sides to solve this equation, we get x is equal to +3. So now we have 2 x-intercepts for that equation, 7, 0, and 3, 0. Those will be the points that the graph of this will touch the x-axis. Okay. To find the y-intercept, we set the other variable, namely x equal to 0. Take 0, substitute in for the x variable in the equation, and then solve for y. 0 minus 5 is -5. The absolute value of -5 is 5, and 5 minus 2 is 3. So our y-intercept is 0, 3. Questions, ladies and gentlemen, how we algebraically found the x and y-intercepts for that absolute value equation. You should also be able to find the x and y-intercepts graphically, okay, by graphing. By graphing.
Yes, Gavin, what?
Okay. So everybody understand how I algebraically determine those x and y intercepts? All right. And does anybody want to see the graphical way of finding these, or are we confident we could type that in our equation editor and use either the 0 or the value function to find those? All right, ladies and gentlemen, that brings us to classwork number 1. Today's date is February 2nd, Groundhog Day. Did Phil see his shadow this morning? Anybody?
Yeah.
So what does that mean?
They said 6 more weeks of winter.
which we normally get anyways. Do you agree? More winter, yeah. Is that meteorologically accurate, ladies and gentlemen? If a groundhog sees his shadow in Pennsylvania, that predicts what our winter is going to be like for the rest of our country? Well, some people beg to differ, but it gives us something to celebrate. You agree? It breaks up the blouse of winter. It's Groundhog Day, so we all have to watch that movie with Bill Murray in it. Groundhog Day. You ever see that movie? All right.
Great.
All right, ladies and gentlemen, this is classwork number 1. See if you can do these problems here. I'll give you some time to work on them. Classwork number 1. Okay. Okay, how are we coming on these, ladies? I'm gonna need more time. Number one, anybody get the distance in exact form for number one between those points? All right, I got a distance of 7 times the square root of 2. Did anybody get that distance?
Yes.
All right, how about the midpoint? Did anybody get the midpoint correct?
Yes.
All right. Number 2, we want to graph this equation. I indicated the values for X I wanted you to use. Therefore, I cranked out all the Y coordinates for all these values. These would be the points that would then lie on the graph of this equation. The X-intercept would be -2, 0. There would be the Y-intercepts, 2 Y-intercepts. Did anybody, are these points looking familiar? Same on your paper?
Yes.
When you plot those points, you graph that thing, it's going to be a parabola opening to the right. Anybody get that graph correctly? It's going to be a parabola opening to the right. Okay. So this is a quadratic function and a variable y, not x, and this parabola opens to the right. All right, any questions on number 2? Number 3, graphing this absolute value equation. Did you get these here? Notice when you try to plug -4 into your equation, you do not get a solution. There is no solution to this absolute value equation when you put -4 in for X. Okay. Now solutions start picking up when X is equal to -3. Okay. Do these points look familiar? Plotting those points, you should see a graph that, oh, by the way, the X and Y intercepts would be these right here. That would be the X-intercept and the Y-intercept. There's 2 Y-intercepts, 1 X-intercept. When you plot these points in this table, did we get a graph that is a V-shaped graph that opens to the right? Did we get that? Notice this equation is undefined for values of X that are less than -3. All right, ladies and gentlemen, so that's classwork number 1. All right, so you can get that to me via email if you want by midnight tonight, that'll be fine. All right, next section 2.3 involves functions and relations. So 2.3, functions and relations. All right. Definition. What's a relation in mathematics? A relation, ladies and gentlemen, is a set of ordered pairs. A relation in mathematics is a set of ordered pairs. Here's an example. Here's an example of a set of ordered pairs. So that would be a relation by definition in mathematics. That's a relation. So any set of ordered pairs constitutes or defines what's called a relation in mathematics. When we speak of relations and functions, oftentimes we're interested in 2 very important sets: the domain and the range of a relation or a function. The domain, ladies and gentlemen, of a relation or a function is nothing more than a set of all X coordinates or input values. The range is nothing more than a set of all Y coordinates or output values of a relation or a function. Domain and range. So for my relation above here, what would be the domain? It's the set consisting of all x coordinates. 2, 3, 4. You do not have to list 3 twice. 2, 3, 4. That's the domain. Notice the domain of this relation is a finite domain. What would be the range, denoted as uppercase R? The range would be the set of all the y coordinates. That would be 2, 5, 6, and 9. Any questions about any of this so far? All right, what's a function then? Well, a function is a special type of relation in which no two different ordered pairs have the same x coordinates. So a function is a relation in which all x coordinates of all ordered pairs are unique. No repeats, no repeated x coordinates. If you have two unique points in a relation that have the same x coordinates, then your relation is only a relation. It's not a function. So a function is a special type of relation. No duplicate x coordinates. Here's an example. Here's an example of a relation, but this relation also is a special type of relation called a function. Notice you do not have any duplicate x coordinates. All the x coordinates are unique. That's why this relation is a function. The domain of which would be what? What would be the domain of this function? Well, it would be the set consisting of all x coordinates. 0, 1, 2, 3, and 4. 0, 1, 2, 3, 4. The range would be the set of all y coordinates. -40. -5, 9, 10, and 16. Okay. Any questions about what a function is? All right, so a function is a special type of relation. All right, ladies and gentlemen, relations or functions are often represented not as a set of ordered pairs, not necessarily. Sometimes they are, but normally they're not. Sometimes they're represented with a graph. So relations and functions are often represented as graphs. Well, how do we know if a graph is a function? How do we know if we're staring at a graph, which is a relation in mathematics? How do we know that graph is a special type of relation known as a function? Well, it's a very easy thing to determine. We can subject the graph to a test called the vertical line test. The vertical line test is used to determine if a relation's graph qualifies as being a function. It's a very easy test to administer. So how do we administer the vertical line test? Well, what we do is we take a hypothetical vertical line, and if we place that vertical line anywhere, ladies and gentlemen, in the XY plane. So if you take a hypothetical vertical line and you place it anywhere in the XY plane, and if that vertical line, no matter where it's placed in the XY plane, touches the graph and at most one point, then the graph is a function. We say the graph passes the vertical line test. If a vertical line placed somewhere in the XY plane touches the graph in more than one point, then the graph is only a relation. It's not a function. Any questions about the vertical line test? All right, let's see if we can put it to work. Let's go to our book and go over problems 15 through 32. All right, 15 through 32. Wrong section. We're now in section 2.3. Uh-huh. I got timed out. I'll have to log back in. Bear with me for a sec. All right. All right, so we're going to go down and we're going to look at problems 15 through 20, 15 through 32. All right. So later on, problem number 15 is the graph of a relation in mathematics. Is this relation a function? Yes or no? Does the graph pass the vertical line test?
No,
So you're saying we should be able to put a vertical line somewhere in the XY plane such that it would intersect the graph in more than one point. Is that possible? If you put a vertical line somewhere in the XY plane, does it go through the graph in more than one point anywhere? Well, you know, I can't find a vertical line's position in a plane that would cross the graph in more than one point, not a vertical line. So it looks like this relation may be a what? Looks like it's a function, doesn't it? It passes the vertical line test. How about number 16? Is this relation a function? Does its graph pass the vertical line test?
Yeah.
Yes, it is. That would be a function. How about number 17? Is this relation a function?
No, because it crosses the line in two different spots.
Yeah, you could put a vertical line somewhere, namely what? In the position of the y-axis. Do you agree? You put a vertical line that coincides with the y-axis, you would intersect the graph at 3 different points. So we have 3 different points with the same x coordinates. And remember, a function must have nothing but ordered pairs with unique x coordinates. And so this is not a function, it's just a relation. This graph fails the vertical line test. How about number 18? Is it a function, this relation? Number 18, you know, it looks like these branches become vertical, but they don't, ladies and gentlemen. They constantly move further and further away from the y-axis as this one moves upward and this one moves downwards forever. So this would be a function. You could not put a vertical line anywhere and touch the graph in more than one point. That's a function. How about number 19? This horizontal line, is it a function?
Yeah.
Definitely a function. How about number 20, the vertical line, is it a function?
I don't believe so.
No, because you could put a vertical line, namely through x equals 2. Do you agree? And it would intersect this line at an infinite number of points. This is not a function, just a relation. How about number 21? It's called a step function. Oh, I gave it away. My bad. This step relation, ladies and gentlemen, is this graph a function?
No, because it would intersect at the start and end of each point.
Well, if I put a line through x equals -1, a vertical line through x equals -1, would it intersect this graph in more than one point?
Yeah.
Well, it intersects the point -1, -1, -1. You agree? I'll give you that. But this is a what? This is an open circle. And that open circle at -1, -3 indicates this point -1, -3 does not lie on the graph.
Okay.
So let me, do you want to rephrase that? Do you think this relation is a function then?
Yeah, it is a function.
It is a function because a vertical line placed anywhere only touches the graph at most one point. Now, if these open circles were closed circles, would this relation be a function?
No, it wouldn't be a function
It
if they
would
were
not-
closed circles.
That's right. If these open circles were closed, it would not be a function because we would have like a vertical line going through x equals -1, and we could have 2 different points on that vertical line that have 2 different x coordinates, namely one that has an x coordinate -1, the other one has an x coordinate -3. All right, so this would not be what, a function, correct? This step relation, this is just a relation there. Ladies and gentlemen, is number 23, this relation a function? It's another way of representing
Yes.
the ordered
Yeah.
pairs. Yeah, because
There's
Well,
no repeats.
careful now, how many different ordered pairs do you see in this Venn diagram here? You see
Four.
one ordered pair that is -8, another one that's -8, another one that's -8, another ordered pair which is -8, 6. I think all these ordered pairs have a what? The same x coordinate of a -8, don't they? So this would not be a function, number 23. And if you were to plot all 4 of those points, you would see that they all lie on a what? A vertical line. Do you agree? They all lie on a vertical line. They all have the same x coordinate of 8, -8. How about number 24? Is it a function?
No.
No, because you'd have 2 ordered pairs, 2 different ordered pairs with the same x coordinates, namely -6, 13 and -6, 9. That's not a function, just a relation. Number 25, is this relation a function? Well, we'd have the ordered pairs of 1, 4, 2, 5, and 3, 5. Just because we got duplicate y coordinates, we don't care. All the x coordinates would be unique. There's no duplicate x coordinates. So number 25 would be a function. Number 26, would it be a function, this relation?
Yes.
It would. All the y coordinates are repeats. They're all -4. We don't care if we have repeated y coordinates. It's just the x coordinates that cannot repeat if the relation is to be a function. This would be a function. 5, -4, 6, -4, 7, -4, 8, -4 would be the ordered pairs. And there are no duplicate x coordinates. That would definitely be a function. All right. So any questions with what a relation is versus a function and what a function is or is not? And when a function is just a relation or is a function? Another way, ladies and gentlemen, in which functions or relations are represented is by graphs. Not just by graphs, excuse me, we just got done with those, but by equations, okay? If you look at this equation here in y and x, y equals x plus 1, if you're to take the time to graph this linear equation in xy plane, you would see its graph would be this line. Ladies and gentlemen, does this line pass the vertical line test? Is this relation a function? And you can clearly see that no matter where you put a vertical line would touch the graph and at most 1 point. So this is a function. Hence, y equals x plus 1 is called a function. We say the output variable is y. The input variable is x. X comes from the domain of this function. Y belongs in the range of this function. The definition of this function is the rule that characterizes what happens to an input value into this function. The rule for this function says that when we put something into this function, we add 1 to it to get the output value. Ladies and gentlemen, it's not what you call the input and output variables that characterizes a function. It's what the definition is. It's the definition that characterizes what a function is all about. For that reason, oftentimes we like to use in higher level math, we like to use what is called functional notation. Ladies and gentlemen, instead of calling the output variable y, we tend to call it something else. And so we're going to try to get used to this thing called functional notation. And if you go onwards in mathematics and get into some pre-calculus or calculus, you will work with a lot of functional notation. So we need to warm up to this. Instead of using y as the output variable in an equation, oftentimes we like to use this notation, ladies and gentlemen. It's called f of x. It's called functional notation, okay? You don't read this as f times x. That's not appropriate to read it that way. You say f of x. That's how you read this notation. F of x is just another name for y, okay? It's called functional notation. So if I gave you this function defined as f of x equals x plus 1, and I wanted you to find f of 0, what does it mean to find f of 0? What do you think that means we need to do? F of 0. It means that our input has to be what into this function? We have to put what in for our input variable x? 0? 0 then becomes the input value. Wherever you see x in the definition of this function, you replace x with 0. And therefore, when you put 0 into this function, Add 1 to it, out comes the output value of 1. So what ordered pair did I just generate here, ladies and gentlemen? What ordered pair solution did I just generate for this linear equation? What's the ordered pair? What would be my ordered pair I just generated? I put in what? I put in 0 and got out what?
1.
1. If you put 3 into this function, the output value will be 4. 3 plus 1 is 4. If you put -2 into this function, -2 plus 1, out comes the output value of -1. So here's some other ordered pair solutions to that equation. 3, 4, -2, -1. All these points would be expected to lie in the graph of this function. Okay. You can put anything into a function, ladies and gentlemen. You can even put a variable or variable expression into a function. If I evaluate this function at C, what would be the output? Well, the output's going to be a variable expression called C plus 1. So any point of the form of C comma C plus 1 would be a point that lies on the graph of this function. What if I put the expression A plus H into this function? Well, A plus H replaces X. And the output would be A plus H plus 1. So yes, this video is being recorded and will be available later. This is making sense, ladies and gentlemen. You can put anything into a function. Now, do you think it matters what you call the input and output variable? The answer is absolutely not. Doesn't matter. As long as the definition remains the same, we're talking about the same function. Instead of calling the function y equals x plus 1, ladies and gentlemen, I could call the output variable h of x. Is this function h of x still the same as this function y equals x plus 1? The answer is yes, because the definition is still the same. We're still adding 1 to the input to generate the output. H of x is the same function as y. If I call the output variable h of t and the input variable t, is this function still the same as these other ones? The answer is yes, because the definition is still the same. We're still adding 1 to the input to generate the output. I could call the output variable or the output quantity z of w and the input quantity w. Definition still the same. This function z of w is the same as h of t, is the same as h of x, is the same as y. All these functions are the same. Their graphs would all be identical. It's just that if you were to graph h of x equals x plus 1, you would call the vertical axis the h of x axis instead of the y axis. If you graph h of t, you would call the vertical axis the h of t axis and the horizontal axis the t axis. That's the only difference. Same definition, same function. If, ladies and gentlemen, you change the definition, then you would not have the same function. So in other words, if I come up with this function here, let's say n of z is equal to z plus 2. Is this function the same as all these other ones above? Is this the same function? Why not? No, it is not, because what has changed? Oh, because I'm calling the input variable z and the output variable n of z? Is that the change? Is that what causes this not to be equal to the other functions? No. What's changed, ladies and gentlemen? The definition has changed, because now this function does something entirely different to its input than these other ones up here. This one adds 2 to the input. Do you agree? These functions all add 1 to the input. That's why all these functions are the same function. This one's different though. Its graph would be different than all of these. Does that make sense? It doesn't matter what you call the input and output variable. As long as the definition remains the same, you're talking about the same function. So you could let imagination go wild here. You could call this function here Snoopy. Snoopy of drag is equal to drag plus 1. Ladies and gentlemen, is this function here the same as all these other functions up here? Same function, yes or no?
Yes.
Same function. Definition is still the same. We're calling the input drag. So what? We're still adding 1 to it to generate the output called Snoopy of drag. Definition the same, same function, same graph. In this case, though, you would call the vertical axis the Snoopy of drag axis. The horizontal axis would be called the drag axis. That's the only difference. The graph would be the same as all the other ones. No difference. So do we understand, ladies and gentlemen, that it doesn't matter what you call the input-output variable. It's the definition that characterizes a function, not what you call the input and output variable. All right, domains and ranges. Let's get back to domains and ranges. Of functions from an equation. How can we determine the domain and range of a function if it's given to us in the form of an equation, not a graph, but an equation? Well, in order to determine the domain and range of an equation, ladies and gentlemen, we need to think of an alternative definition for the domain. The alternative definition is, yeah, it's the set of all input values x, but a domain is also defined to be the set of all real numbers for which a function is defined. So when would a function ever be undefined? When is any quantity in mathematics undefined? Well, there's two main situations that come to mind. If you ever divide by 0, you have an undefined quantity. So if a function has you dividing by 0, the function would be undefined. If we ever take an even root of a negative number, it's no longer a real number. It's undefined as far as the set of real numbers is concerned. So like a square root of a negative number, or a fourth root, or a sixth root, or an eighth root of a negative number, the function's undefined. Okay, so let's try to find the domain of this rational function here. When would this rational function get into trouble? It would become undefined if the denominator is ever equal to what? 0. So in order for this function h of x to be defined, ladies and gentlemen, its denominator can never be equal to 0. Hence, x minus 2 has never can be equal to 0, in which case that implies that x can never be equal to 2. So the domain of this function would be all real numbers except 2. If you try to evaluate this function at 2, h of 2, you're going to have 2 plus 6 over 2 minus 2. You're going to have 8 divided by 0, undefined. The function's undefined. To denote this domain, we could use what's called set notation or set builder notation. So the domain of this rational function would be the set of all real numbers x, such that x can never be equal to 2. Or you could use formal interval notation to represent the domain. The domain would be the set of all real numbers from -infinity up to 2, but not including 2, in union with not including 2 up to +infinity. Do we all realize that this set is all real numbers except what? One number, namely 2. Do you agree 2 is not in this domain here? Correct? 2 is not in here because we got parentheses next to 2. All right, that'd be the domain of that rational function. What would be the domain of this square root or radical function? Well, square root functions remain defined so long as you don't take the square root of a negative number. So in order for this square root function to be defined, the quantity underneath the square root, called the radicand, t plus 9, had never better be equal to a negative. So t plus 9 better always be equal to something that's greater than or equal to 0. Which, when we solve this simple linear inequality, that's implying that t better always be greater than or equal to -9. So therefore, the domain of this radical function would be the set of all real numbers t, such that t must always be greater than or equal to -9. If you try to evaluate this function f of t at some value less than -9, like -10, the function is going to get into trouble because it's going to be the square root of -1. And ladies and gentlemen, we know that to be I. I is not a real number. So as far as the set of real numbers is concerned, f of t is not defined at -10. Correct? Undefined. Or using interval notation, the domain would be the set of all real numbers that are strictly greater than or equal to -9. That would be the domain. Any questions how we're determining the domain of an equation, of a function in equation form? Okay. All right. Let's go back to our book. How would we determine the domain, ladies and gentlemen, of a graph? Well, let's look at number 87, which is in section 2.3 in your homework set back there. What would be the domain of this function? Why am I even calling it a function? Does this graph pass the vertical line test? Is number 87 this relation a function? Notice you cannot put a vertical line anywhere in the plane and have it go through any more than one of these blue points. Therefore, this relation is a function, the domain of which would consist of only the x coordinates. This point has an x coordinate of -3. This point has an x coordinate of -2. This point has an x coordinate of -1. This point has an x coordinate of 2. This point has an x coordinate of 3. So my domain would be the set of numbers consisting of -3, -2, -1, 2, and 3. Everybody clear on that? That would be the domain of that function. What would be the range of this function? Well, the range is a set of all x coordinates. This point has an x coordinate of -4. This point has an x coordinate of a y coordinate of -4. This point has a y coordinate of -3. This point has a y coordinate of +3. This point has a y coordinate of 4, and this point has a y coordinate of 5. So our range would be the set consisting of 4, -4, -3, 3, 4, and 5. Questions how we determine the range and domain graphically for this function? Now, what if our graph of our function is not just a finite plotting of points? What if it's like a continual line or curve? How would we determine the domain of number 89? By the way, this relation, is it a function? Does the graph pass the vertical line test? The answer is yes, it does. So this is a function. What would be the domain of this function? What's the smallest value found in the domain? What's the smallest x coordinate of any point on this graph? What would be the smallest x coordinate of any point on that graph? Well, notice this point -3, 3 is not on the graph. It's an open circle. So the smallest you could possibly fathom for any x coordinate on this graph is you could approach an x coordinate of -3, although there will never be a point on this graph that actually has an x coordinate of -3. So ladies and gentlemen, the domain cannot consist of -3. -3 would not be in the domain. So not including -3 up to what? What's the largest x coordinate of any point on this graph? Well, this arrow indicates that this branch of the function's graph goes on forever upwards. And if it goes forever upwards, ladies and gentlemen, what would be the largest value found in the domain? The largest value. Positive infinity. So the domain would be not including -3 up to positive infinity. So the domain of that function in number 89 would be that in interval notation. That's the domain. What would be the range? The range is a set consisting of all y coordinates of all points on the graph. What's the smallest y coordinate of any point found on the graph? The smallest y coordinate. The smallest y coordinate would be on points down here on this horizontal line portion of the graph, whose y coordinates are 1. So 1 is the smallest y coordinate of any point on the graph, including 1. What would be the largest y coordinate of any point on this graph? Well, this graph keeps going up forever. And because it keeps going up forever, positive infinity would be the upper boundary, upper limit of the range of this function. And so therefore, ladies and gentlemen, the range of that function would be in interval notation, including 1 up to positive infinity. That would be the range. Any questions how we derive the range and domain from the graph of this function? How about number 90 here? What would be the domain of this function? Notice I'm calling it a function, so its graph passes the vertical line test. What would be the domain? What's the largest value found in this domain? excuse me, what's the smallest value found in the domain first? Since this branch goes down forever, down to the left forever, the smallest value found in the domain would be negative infinity. So the domain goes from negative infinity up to what? Up to what's the largest x value found for any x coordinate of this point, any point on the graph? What's the largest x coordinate of any point on this graph?
4?
It would not actually include 4 because we have an open circle. So we would have to not include 4. So therefore, using interval notation, the domain of that function in problem number 90 would be right here. This would be the domain from negative infinity up to 4, but not including 4. That's why we got a parenthesis next to 4. Everybody understand how we got the domain of that function from the graph? What would be the range of that function in number 90? What's the smallest value found in the range? What's the smallest y coordinate of any point found on this graph? What would that be? Well, this graph goes down forever, doesn't it? And therefore, the range would go from negative infinity up to what's the largest y coordinate of any point found on this graph? Well, that's going to be on the highest point of the graph. And so what is the largest y coordinate of any point on this graph? So the range goes from negative infinity up to what? What's the largest y coordinate? What's the y coordinate of that high point there?
4.
So the range of this function would be from negative infinity up to 4 and including 4. Hence, we must have a bracket next to 4 because 4 is to be in the range. That would be the range of that function. So we found the domain in the range. Okay. All right, ladies and gentlemen, number 93. What would be the domain for number 93? The domain. What's the smallest x coordinate of any point found on this graph? Well, this left branch goes to the left forever, up and to the left forever. So the domain will be from negative infinity up to what? What's the largest x coordinate of any point found on this graph? Well, this right branch goes up and to the right forever. So up to positive infinity we go. So the domain would be all real numbers. The domain would be from negative to positive infinity. That would be the domain. All real numbers, the entire real number line. What would be the range? What would be the range of this function in number 93? What's the smallest y coordinate of any point found on the graph? That would occur with the lowest point on the graph, which is down here, and its y coordinate is -3. Now, what would be the largest y coordinate of any point found on this graph?
Infinity.
Positive infinity. So the range would be including -3 up to positive infinity. So here you go. That would be the domain and range for number 93, that function in 93. And there you have it. Okay, let's see here. I think we got everything. Let's see, there was one other problem here. All right, ladies, one last problem, number 111 here. They give you the graph of a function here. It's a weird looking function. And they're going to ask us some questions. A, what would be f of -2? We should be able to use the graph to answer this question. What is f of -2? This function f of x has been graphed for us. F of -2 means we put -2 into the function. So -2 inputs come from the x-axis. So if I put -2 into this function, I go on the x-axis over to -2. And then I go down till I hit a point on this graph. Ladies and gentlemen, what's the y coordinate of this point whose x coordinate is -2? What's the y coordinate of this point down here? Project it back to the y-axis. What is it?
-4.
-4. So f of -2 is equal to -4. Everybody got that? F of -2 is equal to -4. You put -2 into this function, you get out -4. What would be f of 3? You put 3 into this function, which means we go on to the x-axis at 3. In this case, we have to go up till we hit the graph. We strike a point on the graph right here that has an x coordinate of 3. What would be its y coordinate? Because that's what f of 3 is going to be. What's the y coordinate of this point? Project it back to the y-axis and you get 2. F of 3 would be equal to 2. Is this making sense how we're getting these? Now I want you to find all values of x for which f of x is equal to -1. Now f of x is the y coordinate. So what would have to be the x coordinates of all points whose y coordinates are -1? So now we go down on the y-axis to -1. And notice we can project to the left from -1 and strike the graph at 2 points, here and here. What's the x coordinate of this point whose y coordinate is -1? What's the x coordinate of this point here? -3. So x equals -3 has a y coordinate of -1. Here's another point here. X equal to -1 has a y coordinate of -1. And there's one other point right here, this point. This point has a y coordinate of -1, and its x coordinate would be +1. So ladies and gentlemen, the values of x for which f of x is equal to -1 would be -3, -1, and +1. What would be the x-intercepts of this graph? Well, if we guesstimate this one, it looks like about -3.4 or something. Another x-intercept would be x equals 0, and that's it. The y-intercepts, there's only one, 0, y equals 0. What would be the domain of this function? What's the smallest x coordinate of any point found on this graph? Well, remember, this branch goes up to the left, up and to the left forever. So the domain would be from what? -infinity up to, and what's the largest value found in the domain? Notice this point does not have an x coordinate of 2 because it doesn't belong on the graph, but this one does. So 2 would still be in the domain. So it looks like the domain ranges from what? -infinity to what? +infinity? What would be the range? What's the smallest y coordinate of any point found on this graph? That's going to occur where we have the lowest point on the graph. That's going to be right here. What's its y coordinate? -4. What's the largest y coordinate of any point found on this graph? Well, here's a high point, but we can go higher than that. In fact, we can go all the way up to what? +infinity. So the range would be from -4, including -4, up to +infinity. The domain would be from negative to +infinity, entire x-axis. Any questions with any of these problems here, ladies and gentlemen? I've covered everything I need to cover out of 2.1 and 2.3. All right, so I will make these sections available for you. And let's see, is there anything else? Oh, that Alex quiz has been opened up. That'll be due by midnight, February 7th. You have 2. How many attempts do you have on that? I think I gave you 2 attempts. Is that correct? And I'll take the higher of the 2 scores. All right. All right, ladies and gentlemen, any other questions? If so, I'll hang on the line for a couple minutes. If not, have a great, safe weekend. Watch the roads. And I'll hopefully see you on Monday. Happy Groundhog Day, ladies and gentlemen.
Mr. O, did you say that since this is recorded, it'll be posted up later?
Yes.
Okay, and then did you say that the classwork will be due tonight at 11:59?
Yeah,
Send it to your
if
email?
you can email it to me by midnight, that'd be great. Sure.
Okay.
Take a picture.
Is-
I don't care what format you give it to me. Just get it to me, okay?
Okay, and when you say email, that's different from Canvas messaging, right?
I believe it is because, yeah, Canvas messaging, I actually have to be, I think I have to actually be online for the chat. You talking about the chat messaging from Zoom?
Yes.
Yeah, that's different there. Are you going
Okay.
to be able to get it to me by email? Look, if you can't get it to me via email, just give it to me on Monday, okay?
Okay, thank you.
All right. Have a good one. Any other questions?
That's all.
All right. Any other questions, ladies and gentlemen? Happy Groundhog Day. If not, I would like to sign off so I can start transforming this video so I can post it. So have a good one.